The first speaker is Professor Laura de Lorenzis. She is one of the leaders in the field. Many of you already know her. So I have a very, very small bio for those who may not know her. She has started her academic career in her country of Italy, and in 2013, she became a professor of applied mechanics at the Technical University of Braunschweig, close enough, I guess, in Germany. And since 2020, she's been a professor of computational mechanics at ETH Zurich. She's the recipient of many, many awards and prizes, including Rilem, L. Medal, and also Euromech Fellow, and also IACM Fellow. These are very prestigious communities of computational mechanics for many of you who are aware of that, these associations. And she is currently the editor of the Computer Methods in Applied Mechanics and Engineering. So many of you been submitting your papers or been reviewing for the journal, and you are familiar that this is one of the most prestigious journal in the computational mechanics. So with that, I guess I'll ask you all to join me, and virtually, I guess, welcome Professor de Lorenzis, and we are ready to hear your talk. Thank you so much for joining.
Okay, thank you very much, Pania, first of all, for the invitation and then for the kind introduction. And thank you, everyone, for joining. I have to say beforehand that I'm recovering from some sickness, so my voice is still a bit, not normal. And I hope I won't have to cough too much during the presentation. If this happens, I'll just mute myself and wait a few seconds and then continue. Anyway, so this presentation is going to be about an exploratory project that we started a few years ago, and this is the PhD project of my student Oliver Bulaki, the first guy in this picture, and he's actually going to defend in about 1 month from now. So he made it through his journey. I think he did a great job, but you'll judge actually maybe more objectively than I at the end of this talk. And at the beginning of this project, we teamed up with a real Lattice Boltzmann expert, but from the field of fluid mechanics, Martin Gaia, who's a professor in Braunschweig, where I was before joining ETH, as Pania mentioned. And so this was the team for this project. How did we come to the idea of using Lattice Boltzmann for solids? Well, first of all, Lattice Boltzmann may be familiar to many of you, especially if you are active in fluid mechanics. It has become very popular and is still picking up in popularity, I would say, because of some key advantages. So first of all, the algorithmic simplicity, and then the excellent scaling in parallelization, especially on GPUs. And both these properties are somehow related to the fact that in Lattice Boltzmann, there's a famous quote that says, all non-locality is linear, all non-linearity is local. I read this the first time in a book by Sauro Succi, but I'm not 100% sure that he was the first one saying this, so I'm not quoting him explicitly here. So right now, in the current landscape, Lattice Boltzmann is widely used in fluid mechanics, in the porous media community, very often also in simulation of additive manufacturing regarding the fluid phase. And there may be other cases. Maybe you also know of other cases. So why did we want to explore Lattice Boltzmann for solids? Well, the first motivation was that hearing about how great Lattice Boltzmann is in fluid mechanics, one wonders, a solid mechanics person wonders, at least I wondered, is it possible to enjoy the same advantages in solids? And the algorithmic simplicity, the possibility to parallelize on GPUs, and this linear non-locality and local non-linearity. But a second motivation, which is maybe certainly not less important than the first one, is that there are many instances where you want to couple fluid and solid behavior. And if you study the fluid with Lattice Boltzmann, it's supposedly much more efficient to study the solid also with Lattice lattice Boltzmann. So such instances are, for instance, fluid structure interaction, boromechanics, additive manufacturing, and so forth. So the idea is, instead of coupling lattice Boltzmann to, for instance, finite elements, in these cases, one might as well do everything with lattice Boltzmann. So this was another motivation. So first of all, what is our philosophy in this work? We view lattice Boltzmann away from its gas kinetic legacy as a mere numerical method to discretize some PDEs. I'll come back to this in a second. Our fundamental design tool for the lattice Boltzmann schemes that we will come up with is asymptotic analysis. And our objectives are the following. We want to be second order accurate in the smallness parameter. We want to be stable. We want to avoid completely finite difference approximations. And we want to be flexible with the range of material constants. Why am I mentioning these objectives explicitly in this way? Is because I didn't do my homework of showing you a literature review on what had been done before us on lattice Boltzmann for solids. We are not the first ones who had the idea to use lattice Boltzmann for solids. There had been quite a few investigations before us, not super many, but quite a few still. But somehow we felt that these objectives were not really fulfilled, or at least not all of them, by the existing investigations. Very often it was not quite clear what the order of accuracy was. Very often stability was investigated empirically and not really proved. And very often there was a mixture of finite differences and lattice Boltzmann schemes. And as we learned from Martin Gaia, in fact, you lose a lot of the beautiful computational properties of lattice Boltzmann if you mix them with finite differences. So we were really keen on keeping a pure native lattice Boltzmann scheme with no finite differences mixed to it. And also there were a few papers where you could study solve some equations, but only for under some simplifying assumptions. For instance, in elastodynamics, if you had an equal wave speed of the bulk and the shear waves, and we wanted to get rid of these limitations in flexibility and be fully flexible. So I'm skipping the literature review, but you can find a detailed one in our papers. And of course, there are more and more papers coming out. So today we will discuss what we've been doing so far. Linear elastostatics was, of course, the first step as a solid mechanician. The first problem you think of is that. And then linear elastodynamics. Okay, so for now we stay in 2D, but there's another student who's picking up from where Oliver is leaving, let's say, and she already worked out the extension of the elastodynamics to 3D. Okay, so I'm gonna start with some basics of lattice Boltzmann. I'll try to be quick on this because half an hour is not a lot of time. Then I'll quickly walk you through the linear elastostatics formulation and the linear elastodynamics formulation, and then I'll conclude with a summary and outlook. So let's go through some basics for those who are not familiar. So let's say the starting point, if one really wants to start from Adam and Eve, let's say, the starting point would be the Boltzmann equation, and the unknown of the Boltzmann equation is the so-called distribution function, which is the probability essentially of finding a particle of a gas, because that's where this comes from, at the location x at time t with the microscopic velocity psi, so the particle velocity psi. And so you solve for this unknown by solving the Boltzmann equation, which looks like this, as you see here. And on the right-hand side, we have a very, very complicated integral, the Boltzmann integral, that I'm not writing down explicitly. The connection to gas dynamics is through some statistical moment of this distribution function. So the zeroth order moment of f, you see, so the integral of f over the velocity space will give you the density of the gas at location x and time t. And if you compute the first order moment, again, so the integral of f times psi, d psi, so again in the velocity space, you obtain the linear momentum density, rho times u of the macroscopic. So here you see a central concept that in lattice Boltzmann, if you have a microscopic quantity, which is, okay, this is not yet lattice Boltzmann, this is the Boltzmann equation, but still we see already that computing statistical moments of the distribution function, you recover macroscopic properties. And this we will find again also in the Lattice Boltzmann scheme, so in the discretized version, let's say. So the first step towards going from the Boltzmann equation to Lattice Boltzmann is to substitute the complicated integral on the right-hand side with a simplified operator, and this is also called collision operator. Now this form that I'm representing here is the simplest possible. It's called BGK from the acronym of the three gentlemen who came up with this formulation, and you see that it corresponds to a simple relaxation towards some equilibrium value of the distribution function with some characteristic relaxation time. Then, so to go in direction lattice Boltzmann, you discretize. So you first discretize in velocity space, meaning instead of having any possible velocity psi, you only admit a finite set of admitted velocities. So you see here a very frequently used popular stencil, so set of discrete velocities from it's called D2Q9 because we are in 2D and these are 9 velocities, including a central velocity equals 0. And you see that already we are depicting a lattice here because these velocities are bringing you from one point in a lattice to another neighboring point of the lattice. And so now that we have a finite set of velocities, we can associate to each of these discrete velocities the corresponding population. Now we don't call it distribution function anymore, we call it population. So for instance, using this stencil, we will have 9 populations, each of which will be associated with the corresponding discrete velocity. And then we discretize in space and time. And this discretization in space is done using this same lattice. And also the discretization in time is done in such a way that at each time step, each population Fi, let's say each discrete population will only be able to move from one point of the lattice within one time step to one of the neighboring points of the same lattice, and according to the corresponding velocity. So we also define a scalar lattice velocity as the ratio between the spatial discretization parameter delta x, so the size of this lattice, and the time discretization parameter delta t, so the size of your time step. Okay, and so this essentially what we find here upon discretization in space and time is the Lattice Boltzmann formulation. Let me just slightly change notation. I'm going to use two subscripts, I and j, alluding to the, let's say, a sort of tensor product formulation where I call I anything that goes in x and j anything that goes in y. So now I and j can be -1 or 0 and 1, so I can or 1, so I can express my velocities from the D2Q9, for instance, in this way, and this is advantageous for the way we write down the formulation. In our work, we actually use two velocity sets. For elastodynamics, we use D2Q8. So this is essentially the same as D2Q9, excluding the 0 velocity in here in the center, because it turned out, as I'll mention later again, that this C00 was irrelevant, and so we decided to get rid of it. In elastodynamics, we're going to use an even simpler stencil consisting of only 4 velocities, so we call it D2Q4. Okay, so what's the path conceptually then from the Boltzmann equation to Lattice Boltzmann? In a nutshell, what we just saw is we start from Boltzmann equation, then we substitute the integral on the right-hand side with the BGK approximation, then we perform velocity discretization and time and space discretization. This is explained in a bit in a sloppy way, but it needs to be quick, and so this is the best I could do in such a short time, let's say. So, and so in this way we went, so not we, but you can go from, this is very classical, all very well known so far, you can go from the Boltzmann equation to the Lattice Boltzmann equation. This figure is a courtesy of Manfred Kravchik, my colleague in Braunschweig. You see he and his collaborators, they put Boltzmann at the computer to emphasize the discrete nature of Lattice Boltzmann, which is then solved with a numerical algorithm. But the interesting thing is that you can so from the Boltzmann equation using Chapman-Enskog expansion, or from the Lattice Boltzmann equation, again using Chapman-Enskog expansion under slightly different assumptions, you can recover Navier-Stokes and continuity equations. And so this is why the Lattice Boltzmann equation is solved to recover eventually the macroscopic quantities that you would obtain by solving Navier-Stokes and continuity equations. And so this is what Lattice Boltzmann is mostly used for nowadays. But in our case, we're going to completely ignore this path from Boltzmann to Lattice Boltzmann. So we really don't care about the Boltzmann equation. Sorry, maybe that sounds a bit disrespectful, but I should say we really start from Lattice Boltzmann, and what we care about is that Lattice Boltzmann can be used as a discrete algorithm to approximate the solution of the desired governing equations. So in our case, elastostatics and elastodynamics. And in order to make sure that by solving Lattice Boltzmann, we are approximating these equations to the desired order of accuracy, we don't use Chapman-Enskog expansion, but we use asymptotic analysis. And so this epsilon is our smallest parameter. We will see it later on again. And so for this parameter, much smaller than 1, then we can show what happens and whether we are able to recover the governing equations that we wish at leading order. Okay. Now, what we need to design here is simply, in quarter quote, our collision operator. So our next objective will be to design this collision operator in such a way to be sure that we are discretizing the target equations. Now, from now on, I'll simplify a bit the notation, and I'll omit the hat, which was meant to distinguish between discrete and continuous quantities, but we're gonna omit it from now on. Okay. So let me write down once more the Lattice Boltzmann equation with a BGK collision operator. This is exactly what we had in the previous slide. Now, very often delta T over tau is also indicated as omega and denoted as a relaxation rate. You can rewrite this quantity on the right-hand side as you see here. And very often one separates the Lattice Boltzmann in 2 stages. One stage is the stage where you compute the post-collision populations as functions of the pre-collision populations and of the equilibrium populations. And of course, this function also contains the relaxation rate. And so essentially, you're computing here the quantity on the right-hand side. And this is a local, so this is possibly a nonlinear operation, but it's always a local operation. So you can perform this operation at every point in the lattice, and you don't need any information from the neighboring points. And then there's the next step, which consists in saying that these post-collision populations are set equal to the populations at the neighboring points, and according to the respective velocities. And so this is the so-called streaming step, where you're moving your populations from one point in the lattice to one of the neighboring points of the lattice according to your the velocities in your stencil. So this step is non-local because you're streaming the populations, but it's always linear. So essentially, it's always this very simple operation that you see written here. So here you see this graphically. Here you see the populations in this point are indicated with using a D2Q9 are indicated in black, and the population, one of the populations at each of these points is denoted in blue. And during collision, these populations are changed according to this first formula. But during streaming, they will just move place, and in this case, they will just switch places because the velocities are going to in this way from one point to the neighboring point and vice versa. Okay. So this motivates what the statement that I was writing at the beginning, that in Lattice Boltzmann all nonlinearity is local and all non-locality is linear. Okay. And this is again a picture that depicts this simple concept. So now, to conclude for this introductory simple part, So as in the Boltzmann equation, you can also, after velocity discretization, you can compute statistical moments now of the populations. And again, so you can compute zeroth order moment, first order moments, second order moments. For instance, in fluid mechanics, the zeroth order and the first order moments would be the so-called conserved moments, meaning they will not be relaxed to equilibrium, so they will be set equal to the equilibrium values, and this will correspond to the macroscopic quantities that are conserved, so the density and the linear momentum density. And notice that in BGK, these second order moments, which are relaxed to equilibrium, they will all be relaxed with the same relaxation rate. In general, you can compute moments of any order, but also you cannot compute any arbitrary independent number of moments, because you will always have as many independent moments as populations. This can be very easily checked using this formula. For instance, for D2Q9, you see you have 9 moments in total, 9 independent moments. Okay, so now let's quickly go through the formulations for linear elastostatics and elastodynamics. We've started with periodic problems. I'm not going to handle boundary conditions in this talk, because those would require a talk on their own, and they are pretty much a hassle in Lattice Boltzmann. But we started with periodic problems, and then we have a paper that was just devoted to boundary conditions for elastostatics. So if you're interested, I'll give you the QR code at the end. So, in linear elastostatics, you can combine balance of linear momentum kinematics and the constitutive law into the famous Navier-Cauchy equation, complemented in this case with periodic boundary conditions. Now, you may have noticed that Lattice Boltzmann is intrinsically a method that has a time stepping. So it's an explicit method based on let's say, a time stepping. So that means we cannot solve an elliptic equation in one shot as we do with finite elements. So we need to incorporate some time stepping, and how to do it was proposed by a previous paper, and we are using here the same approach. So we are adding a fictitious term on the right hand side, which contains a time derivative of the displacement. And then, okay, we are non-dimensionalizing everything, which is something that's always a good idea to do. Plus, in Lattice Boltzmann is also done very often. Now, for linear elastostatics, I'm just telling you what the result was of the process of design of this collision operator, because it would be too long to go through the steps of derivation, but you find them all in the paper. So the result was that we cannot use a single relaxation time collision operator like the BGK that I showed before, because we wouldn't be able to have enough flexibility to calibrate separately the two elastic constants of isotropic linear elasticity. And so we resorted to the so-called multi-relaxation time collision operator, which has been known for a long time. So the basic idea is to let different moments relax at different rates, and so we could exploit this flexibility. So you can exploit this flexibility not only in our application, it's also exploited sometimes with fluids. In fluids for accuracy and or stability. So in our case, it was exploited to allow the bulk and shear modulus to be calibrated both in an independent way. So the consequence of using a multi-relaxation time is that you need to perform the relaxation in the moment space. So first you need to convert the populations to moments, relax them, and then convert the relaxed moments to relaxed populations after collision. This is not a difficult operation. This is essentially you go from populations to moments just by multiplying by a matrix of constants. So it's a very straightforward operation. So this is, let's say, the conceptual flow of the collision. You start with the populations before collision, you obtain the moments before collision, then you relax. So you conserve some moments, you relax others with appropriate relaxation rates, and then you again multiply by the inverse of that matrix I was mentioning and obtain the populations after collision. Now, one design choice is what should be the moments that need to be conserved and what should be the moments that need to be relaxed. And then, so this is the first choice, how to choose the conserved moments. And the second choice is how to design the equilibrium moments and the relaxation rates of the moments that need to be relaxed. Now, without going too much into details, you see here the results. They are motivated in a very detailed fashion in the paper, but the bottom line is we know exactly what to conserve. So essentially, in a nutshell, being a little bit sloppy because there are some details involved which I'm not mentioning, the two components of the displacement field are identified with the two first order moments, and the remaining moments are relaxed with these expressions of the equilibrium moments and these expressions of the relaxation rates. And this comes everything from asymptotic analysis. So in asymptotic analysis, what you do is you use an expansion ansatz for the populations in a smallness parameter, which is the epsilon I was mentioning before. And since here you need to expand both in time and in space, you need to make an assumption on how the space ansatz and the time ansatz relate to each other. So in this case, since we have first order derivatives in time and second order derivatives in space, the most natural assumption is the so-called diffusive scaling, where the smallness parameter square goes like delta x square goes like delta t. Okay, the procedure is quite tedious and long because here we have a multi-relaxation time setting, which makes things not super easy. But in a way, once it's clear how to proceed, it's also conceptually relatively straightforward to do. In terms of stability, our main tool in this case was von Neumann stability analysis. Without again going into super many details, I can tell you that whenever we have relaxation rates between 0 and 2, stability is given, and we can also construct stability maps which relate the elastic constants nu and e, but notice that this e is a scaled e which contains the kappa constant that is at the right hand side multiplying this fictitious time derivative, and so we have actually some flexibility to move along the horizontal axis. So for a given nu, we can pick kappa in such a way to be within the stable region. Yeah, and there's also a very tiny unstable region here close to the incompressibility limit. Notice that here we are doing things in pure 2D, so ignoring completely the third direction, so neither plane stress nor plane strain, but pure 2D, which is the reason why our nu ranges up to 1 and the incompressibility limit is 1. So in case you're puzzled by not seeing 0.5 here, but 1. So we concluded, in fact, that the method is accurate and stable for all nus between minus 0.3 and almost up to the incompressibility limit 1, so 0.95 more or less. Okay. Now, we wanted to check, of course, that things are as we expect. So here you see that the error decays. So we are plotting both L2 and L infinity error in the displacement and in the stress. You see that you need a certain number of time steps, but after this number of time steps, you converge to the steady state solution. So at this point, this fictitious time-dependent term at the right-hand side disappears, and you will get the steady state solution that you would obtain if solving the elliptic equation in one shot. And we checked convergence, second order, in displacements and stresses, which is a quite striking and, I mean, nice surprise for people used to finite elements, and so used to stresses converging always one order lower than displacements. And so in Lattice Boltzmann, this is not the case. So both displacement and stress converge second order in L2 and in L infinity. And it's nice to compare with finite elements. You see here that if you look at the finite element displacement error, you're here. The finite element stress error is up here, goes down, of course, first order with linear elements. And the constant is also relatively bad for this example. But if you look at Lattice Boltzmann, you are down here. So you gain quite a bit of accuracy, especially in stresses because of the larger convergence rate. Okay. Yeah, and then, okay, we added then some more general boundary conditions, Dirichlet, Neumann. This was actually quite a bit of work. Eventually it turned out to work well. So here you see a slightly more physical example. The previous ones were all manufactured solutions. This is a classical plate with hole where we could recover the expected solution quite well. Now going quickly to elastodynamics, I think my time is almost up, so I need to hurry. So here we don't need to embed any fictitious time dependency because we do have a time dependency in a natural way. So once again, we look at the Navier-Cauchy equation for the dynamic case, again with periodic boundary conditions, and of course now we also need some initial conditions. Here, key for us was to reformulate the problem as a first-order hyperbolic system, which is something that we found in previous work that you see quoted here. There may be more, in fact, and even earlier, but these are two recent contributions where this reformulation was proposed. And so essentially now we have our unknown that is no longer the displacement field only, but we have the two components of the velocity field, plus we have these three fluxes, which are connected, in fact, to the three components of the symmetric stress tensor in 2D. And so we have 5 unknowns now for a first order hyperbolic system. And in this case, okay, we non-dimensionalize as usual. And in this case, we decided to solve the problem by using vectorial Lattice Boltzmann, which is a relatively recent variant of Lattice Boltzmann, still much less popular than the scalar lattice Boltzmann, but still keeping all the advantageous properties of scalar lattice Boltzmann from a computational standpoint. And so the bad news is, of course, here we have 5 unknowns, but the good news is we can use a very simple stencil, so just 4 velocities, as I was anticipating some slides ago. And the other good news is we are good off already with a simple BGK. So we have more unknowns, but we have less velocities and a simple collision operator with one relaxation rate, which makes our asymptotic analysis much easier also. So again, we don't need to relax in moment space. We can relax directly in population space. So we need to design the equilibrium populations, the relaxation rate, and the initial conditions, again, with the wish of being second order consistent. So the final results coming from asymptotic analysis look like this, maybe not super friendly. I have no time to go into details, but every detail is in the paper. The relaxation rate is 2. This is the equilibrium. These are the equilibrium populations. And also here you see how to embed the forcing. And these are the initial conditions. And so essentially the conclusions from asymptotic analysis is that you obtain second order consistency on periodic domains using this D2Q4 to the power 5, in the sense that every population is a vector with 5 components, velocity set. If you use the zeroth order moments, equilibrium populations, and also the initial conditions that I showed in the previous slide, in this case, it's much more natural to use acoustic scaling because we have second order derivatives in the PDE with respect to both space and time. And yeah, and the rest I already mentioned. Okay, now in the case of stability here, it turned out that von Neumann didn't really help. It gives you a necessary but not a sufficient condition. So we investigated stability using a notion recently proposed in some papers, the notion of pre-stability structures. And I spare you the details. I wouldn't have enough time anyway. But what turns out at the end is that stability can be proven under a condition that really resembles the what we know very well from explicit dynamics already, for instance, in the finite element method. So a sort of CFL condition, and this we also verified with some numerical examples. So once again, you see we are second order consistent in displacement and okay, in this case in velocity, but then with the trapezoidal rule, you can integrate the velocity and obtain displacements, keeping the second order, and also in the flux quantities, which correspond to stress components essentially. So here you see another example. So to conclude briefly, so we developed these 2 new Lattice Boltzmann formulations, one for linear, or Oliver actually, I should say, it's really his work, for linear elastostatics and for elastodynamics. He published 3 papers. We published together 3 papers, one on elastostatic for periodic boundary conditions, one on boundary conditions for elastostatics, and the most recent one on elastodynamics. where we have some boundary conditions, but very restrictive ones. So really, this is mostly work done for periodic problems. The elastostatic formulation is based on multi-relaxation time, and the elastodynamic formulation is based on vectorial lattice Boltzmann. In both cases, the fundamental design tool is asymptotic analysis. Both formulations are second-order accurate and provably stable so far in 2D, but as I mentioned, 3D elastodynamics is ready. We still have to generalize boundary conditions in the elastodynamics, and in the future, I mean, after this exploratory work, let's say the curiosity is really to understand whether this can become a competitive tool in computational mechanics for solids. So of course, in order for it to be such, it needs to be able to tackle nonlinearity, couple problems in 3D, and we need to really prove whether the performance is the one we expect by testing in high-performance codes. So there's still a lot to be done, but it's also an exciting area, for at least for me, for us, because it's still fairly new, and there's still, you know, I think there are opportunities here, because this may indeed become a really competitive tool on GPUs for future computational mechanics. And so with that, I'd like to thank you for your attention, and I'd be happy to answer questions.
Thank you so much, Laura, for a wonderful talk. And thank you for introducing us to the new field. You basically actually answered, I guess, many of my questions as part of your future work. But there are two questions in the chat that I'll start with them, and then whoever else has question, I guess maybe we'll get to them. So one of the questions is coming from Whiten, and he said that he's been working on using OpenLBM method, and he's asking if we can couple LBM with DEM to simulate for nanoparticle. And he said that I know LBM is suitable for solving nanoscale problems. So is the above idea feasible?
So, to be honest with you, I don't know. We never tried, but this is one of the things that definitely I think would be nice to try. So, yeah, but I don't have, let's say, any educated guess of what could be possible issues, because yeah, we never tried. There are so many things we never tried, and so yeah, if you need any, I mean, if you want to try, and if you need any help with the Lattice Boltzmann parts that I presented, I think we would be excited to collaborate with anyone interested on using this approach. I cannot see why it should not work. I don't know what currently is done there, but yeah, but yeah. So sorry, it's not really maybe a very helpful answer, but I also don't know a lot about the question. So
Yeah. Yeah, so yeah, maybe he can reach out and then start some discussion offline. So another question is coming from Azad Sheidai, saying that thanks for your presentations. What's the advantage of LBM over FDM for elastodynamic problems where we model wave propagations in solid media for applications like ultrasound modeling and so on?
yeah, I mean, so typically FDM has the limitation of being able to represent arbitrarily shaped domains, right? So typically this is what is mentioned as the drawback of FDM, and there LBM, in fact, if you have properly designed boundary conditions, is super flexible, so you can handle really arbitrarily shaped domains. So I would say that with LBM, you should be more flexible. Having said that, I mean, I never tried. We never tried FDM for elastodynamics, but I would say that LBM there should be a much more flexible choice.
So the other question is coming from Bahadur Bahmani, and is thanking you for the great talk. He's saying, I'm just trying to learn more, and it seems to me that in the end, we need to be able to write down the governing equations in their full global form, like Navier-Cauchy equation, where constitutive laws are first inserted into the PDE, maybe for asymptotic analysis. Is it possible for problems like plasticity, where there is an intrinsically local process?
So let's say we proceeded this way for convenience primarily. So it's not that we had to substitute everything, but it was just more convenient. But on the other hand, if you look at the vectorial approach, in the vectorial approach, this is not really done because if you look at the unknowns, essentially for me, coming from the finite element community, the vectorial approach looks a bit like a mixed method where essentially the stresses are also discretized on top of these displacements, a sort of sigma U method in a way, if you want. So I think that, okay, plasticity is definitely an interesting outlook, and we still haven't even given a thought to plasticity, honestly. But I don't think that this would be a no-go. I don't think we would really need to have the possibility to write in let's say the governing equations, plugging everything inside one set of equations. I think we could still leave them separate as we do right now, and we would still be able to run asymptotic analysis. But of course, I'm just guessing because this we haven't tried. So, but let's say I don't see any stringent reason for having all the equations plugged into each other to have a unique set like we did with Navier-Cauchy. In that case, it was possible to do. We did it, but it's not, a stringent requirement of the approach. I hope this answers your question.
So I guess the last question is coming from our very own Florin, and
Hi, Florin.
he's asking, on periodic problems, how would this compare against the spectral methods? And he's also thanking you for your great talk.
Thank you very much. Yeah, good question. I have no idea. We didn't run any comparison so far. In fact, we didn't run any comparison neither against spectral methods nor against finite elements, which actually should also be pretty competitive in elastodynamics. So yeah, it would be very interesting to run this comparison and see what the pros and cons can be. But right now, I really don't know. But thanks for the question. It's actually an interesting question. Yeah, they're all interesting questions, by the way. Thank you, everyone.
Well,
Thank you very much.
well, thank you so much for the wonderful talk. And then the purpose is just creating these discussions and hopefully some collaborations. People, they will be, hopefully you are open that people to reach out to you if they
Absolutely
inspired and they want to continue this with their own applications or their own areas of interest. So so I guess let's thank the speaker one more time. Thank you so much for the great talk.
very much. Thank you very much.
So, and if there are more questions, you can stay on, and then at the end we'll take some other final questions. So for I guess now it's time to move to our second wonderful speaker, and if you can, yeah, so good. So the second speaker is Dr. Pablo Seleson. He's currently a research scientist in the computer science and mathematics division at Oak Ridge National Laboratory. He got his PhD in computational science at Florida State University in 2010 before joining the Institute for Computational Engineering and Science, known as ICES, at the University of Texas at Austin. So his primary research area is mainly on multi-scale material modeling and mathematical and computational analysis of paradynamics and some other non-local models with applications to computational fracture modeling, which many of you most likely are interested among these audiences. So with that, I guess I'd like to welcome Pablo, and we are ready to hear your talk. Thank you so much.
Thank you, Pania. So thank you very much for the invitation to give a presentation at this innovative seminar of the Novel Methods TTA. It's really a great pleasure to be here. So I would like to talk about what they call breaking through, which is harnessing exascale computing and peridynamics for complex fracture modeling. So I'll begin with an introduction to peridynamics for those who are not very familiar with it. And then I'll briefly discuss coupling peridynamics with classical continuum mechanics with one goal is to reduce computational cost. And then we'll move into discussing a new code we are developing that is exascale capable. It's called Cabana PD, and then show some numerical examples. So the motivation for peridynamics is failure and damage in materials. And here we can see two famous cases of catastrophic failure, such as a bridge collapse in 1940 and a fracture in a famous ship in 1943. So what we would really like to do is to develop advanced modeling tools that can help us understand, predict, and ultimately prevent material failure. Now, going back to the basics, computational solid mechanics is the field that employs computational methods to study how bodies deform, and the finite element method has become the primary choice for large-scale engineering simulations. Now, reviewing some properties of the finite elements, basically, we employ a mesh discretization of a continuous domain into a discrete set of elements. And it allows us to simulate large-scale systems by employing polynomial shape functions to interpret displacement within elements. And also, displacement continuity is assumed between elements. And what this tells us that material failure and damage simulation with the traditional FEM requires special techniques to represent fracture surfaces. So some alternatives to the traditional FEM have been proposed. Here are some of those methods. For example, the inter-element separation method allows fractures to develop and propagate in between elements, but not through the elements. However, more other methods such as the enriched FEMs, such as the XFEM, the PUM, and the GFEM, introduce enrichment to the basis functions, so it allows to represent discontinuities between elements. Now, a different class of approaches tries to remove challenges that has to do with meshing dependence on cracks and some of the complications associated to the mesh, and they introduce mesh-free methods. For example, SPH or RKPM or FPM. And here you can see an illustration of how on finite elements, the basis function is built on top of mesh, but on a mesh-free method such as RKPM, the basis function is built independently of any mesh. Now, there are other methods, of course, such as the element erosion, phase field, and others. Now, note that these methods rely on classical continuum mechanics, which actually has a fundamental mathematical deficiency for fracture modeling. And this can be observed in the governing equation, where, because of the presence of the differential operators, we need spatial derivatives. So one way to approach this differently is by trying to reformulate the mathematical equation. And this is where peridynamics comes into the picture, which is a non-local reformulation of classical continuum mechanics suitable for material failure and damage simulation. So in peridynamics, as in many other non-local models, what you have is every point x in a material, it's assumed to interact with some surrounding within some neighborhood we denoted by h sub x of radius delta, which is called the horizon. It's a length scale in your material. And then we follow this evolution equation where rho is the mass density, u is the displacement field. And then on the right-hand side, I have an integral operator instead of a differential operator, which integrates a force function f that determines the interaction between every pair of points in your material. And then we have b is the body force density. So the key thing here is that this force function f does not require spatial derivatives. Now, peridynamics has been proposed in the year 2000, and over the first couple of years has been grow very, very fast. Actually, we have a paper where we study the evolution of the peridynamics co-authorship network, and among many other results, one thing we realize is that it has been an exponential growth both in the number of publications and the number of authors. So it's a really fast-growing field. Now, in peridynamics, the force function can be described in its most general form with this difference of two operators. One is called the force state evaluated at x, and the other one is the same evaluated at the point x prime, which is the neighbor of x. And this operator takes what we call a bond, which is this vector of x prime minus x, and maps it to force per unit volume squared. And there is different type of force functions one can come out with. One can distribute in one way, it's by talking about ordinary versus non-ordinary material models. In ordinary material models, the force operates along the line connecting the 2 points in the deformed configuration, and this can come into two forms, either a bond-based, which is a pairwise type interaction form, or a more general, which is called the state-based. And also we have non-ordinary material models, which are also state-based, where the force function can operate in a direction that is different from the direction connecting the 2 points in the deformed configuration. So just to remind, this vector x prime minus x, we call it a bond. So this concept of bonds in peridynamics will come often later as well. Now, let's review some of the common material models that people use. This is a basic one for brittle elastic materials. It's called the prototype microelastic brittle material. It's an ordinary bond-based model where the force function depends on a bond-breaking function, which allows us to represent fractures, a bond constant C, which can be related to the bulk modulus, and a stretch, which is the relative change in the elongation of the bond, and this is a measure of strain. And because this is an ordinary material model, we have here the direction given by the deformed bond. Now, there's different mechanisms or methods one can use to introduce fracture. We call it bond breaking, and one of the criteria that is commonly used is called the critical stretch criterion. And in this case, wherever the stretch exceeds some critical value given by S naught, we change this bond breaking function mu from 1 to 0, making the force to be 0 between these points. And the critical stretch can be related to the fracture energy G0. So now more sophisticated or more general material models can be state-based models. For example, we have the linear peridynamic solid model. It's actually a nonlinear model, but has linear dependence on its functional form. It has a volumetric term and a pairwise term. And here K and G are the bulk and shear modulus, and theta is the dilatation. And we also have in the non-ordinary state-based models, the classical correspondence models, where we have a direct dependence to the classical stress tensor, which now it's evaluated using an approximate deformation gradient, and here K is the shape tensor. So this framework allows us to also incorporate existing complex material models. Now, one feature of peridynamics, which is desirable, is consistency with the local theory under certain assumptions and in certain limits. So if you make an assumption on smoothness on the deformation and the material model, we can express the integral differential equation as a partial differential equation, as given here, which resembles classical continuum mechanics, except that now there is a dependence on a non-local stress tensor, which when we take the non-locality to vanish, so delta goes to 0, we recover a Euler-Kirchhoff stress tensor. So there is a nice connection to the local theory. To illustrate this with a simple example, let's take a look at the one-dimensional linear model for a particular choice of C, which depends on K, which is a classical constant, and the assumptions of smoothness on the displacement U. We can do a Taylor expansion and obtain here a high-order gradient PDE, where the high-order terms depends on powers of delta. So actually, there are many length scales here. But then if we take delta to 0, we see how all these high-order terms vanish, and we record the classical wave equation. Now, in terms of convergence, actually, because we have this additional length scale delta, there is different ways to discuss convergence in peridynamics, and in particular, in general, in non-local models. So we have already showed the convergence from the continuum non-local model to the continuum local model by taking delta to 0 under certain assumptions. We already showed that. Now, in the standard PDEs, you take H to 0, like mesh or grid refinement, and the discrete model recovers or reduces the local, the continuum model. So we have a similar approach also in non-local models where you can fix your non-local parameter delta and then take h to 0. And then we also have what's called asymptotic compatibility, which means like the discrete non-local model reduces to the discrete local model, but also there is an inversion where you can take both length scales, delta and h, and jointly take them to 0 to get from the discrete non-local model to the continuum local model with certain assumptions on the rate of convergence. Now, in order to compute fractures, well, we need to discretize. So P-dynamics is a continuum formulation, so you can discretize with many methods. Here we are showing the mesh-free approach proposed by Sealing and Ascari in 2005, where you discretize your domain with a set of computational nodes in blue, and then you evaluate with the collocation approach your governing equation at each of those nodes. So every time you have x, it's replaced by I, and then the integral is effectively replaced by a Riemann-type summation with weights given by either the cells representing each of the nodes or some partial part of that cell. And with those, we can run very much a lot of simulations. So here is an example of a projectile impact on a brittle disk. What we are not seeing here is the projectile, but we see the result of the impact. We are visualizing this by having a variable at each node that represents damage, and this allows us to post-process the fractures without having to track the fractures, which is a very highly desirable property. Similarly, we can look into a case of a microcrack propagation in a polycrystal. This is a very highly complex system at the micro scale level. And here we obtain, by applying tractions, we obtain initiation of the cracks, propagation with a complex network of cracks. We obtain initiations on multiple sites. And this technology, it's very suitable to handle this type of highly complex crack scenarios. However, one of the limitations, or at least some challenge in P-dynamics, is computational cost. So as you can see here, where the ratio between this length scale, the non-local length scale, and the grid spacing is 2, you already have 32 neighbors per each computational node. If you move to a ratio of 3, you reach more than 100 neighbors. And if you do one step of grid refinement, you go from 3 to 6, and then you get nearly 1,000 neighbors. So P-dynamic neighborhoods can easily exceed 10 times those of other particle codes. So one interest approach here is to try to come up with methods to mitigate or reduce computational cost. So one approach that has been quite popular is to reduce computational cost by restricting P-dynamics around the cracks and then coupling those to the local theory. So here is an example where we have a crack, we have a region surrounding the crack where we can use P-dynamics, and then we can transition to classical continuum mechanics because we know that P-dynamics behaves like classical continuum mechanics in the case that we have smooth deformations. And then this allows us to combine the strengths of P-dynamics and the expediency of classical continuum mechanics. Now, the components of such a coupling are as follows. First, you need to have physically consistent models to couple, but we know how to do that because of the consistency in the conversions of P-dynamics to the classical models, so we can identify both. Then you need to come out with proper coupling methods, and this may or may not be the same for static or dynamic problems. And because cracks propagate, you may need a model adaptivity mechanism to be able to evolve subdomains as the cracks propagate, and also identify the critical regions where you need to use the P-dynamic model. As well, there are some coupling artifacts that may appear that one needs to take care of. For statics, this can come in the form of a patch test failure, the inability to pass linear solutions, a lack of energy preservation, and then in a recent paper, we have identified a new type of coupling artifact, which we refer to it as a lack of the overall equilibrium. And in dynamics, you can observe artificial wave reflections on the interface, as well as lack of conservation principles. So we have a review article where we went over very different coupling methods, and I'm not going to go over all these methods, but just show you that we were able to identify coupling methods as what we call constant horizon ones versus the varying horizon ones. In the constant horizon ones, we have two categories: generalized domain decomposition methods, such as the optimization based on the partition procedure. And then we have a few coupling methods that resemble those from the atomistic to continuum coupling literature, which is also has been a very active field. And for this, we have what's called the Arlequin, the morphing, the quasi-non-local, the blending, and the splice methods. And in the varying horizon, we have energy-based versus force-based methods. The force-based methods try to couple governing equations, and the energy-based methods try to couple energies. In the energy-based, we have the shrink horizon approach, and in the force-based, we have the partial stress. I'm not going to talk about this, but I'm going to give you a little bit of discussion on the blending and the splice, just so you can get some illustration of this. The other thing that one has to consider is a domain decomposition for the coupling. So this is a general coupling configuration in 1D and in 2 dimensions. You would normally have like a non-local region, a local region, and a transition in between the two. And this can come in different forms. For example, on the 1-dimensional, we have what's called adjacent domains. But in the 2-dimensional, one can have both adjacent domains, but also embedded domains. In this case, we are embedding the non-local region within the local region. There is a transition in between. Now, note that different coupling methods use different domain decomposition, so you have to adapt it to the type of method you use. So let's discuss one example of a static plate under tensile and shear loading. As you can see, the representation on the left, and we have a rectangular slit at the center. And what we are going to do is we are going to surround the slit with a peridynamic region. Then we are going to have a blending region surrounding it, and then transition to classical elasticity. So we have classical elasticity adjacent to the boundaries. We have internally a peridynamic region, and then there is a blended model used in between. And the way to do that is we introduce a blending function that takes the value of 1 in the peridynamic region, 0 in the classical region, and a transition between 0 and 1 between the two. And with that, this allows us to develop a blended model. Here is a result. What was nice about this model is that we started just from the full peridynamic description of the entire domain. We introduce a blended function, doing some assumptions on the deformation. We're able to naturally derive this blended formulation. And as you can see here, the blue part is the peridynamic contribution. All the green are the introductions of the blending function, and then the red is the correspondence to the classical elasticity. And one of the features of this model is that if you pick beta to be 1 everywhere, you recover peridynamics, and if you pick beta to be 0 everywhere, you recover classical elasticity. So actually, the blending function can help you determine where iteration should be, and also could be a tool for adapting the evolution, because it's actually the same equation used everywhere that takes different forms depending on the values of the blending function. So this is one result. On the left, we have the classical model. On the right, the peridynamic model, and the middle, the blended model. On the top, we see the actual deformation on the full plate. And on the bottom, we zoom in around the hole at the center. You can see that the classical model is very fast. In this case, it's just 2 minutes. On the right, it takes about 4.3 hours with peridynamics. And by combining the two, we can reduce to 24 minutes by still allowing that to capture the features of peridynamics around the center of the hole. So you can see that outside from the hole, the deformation looks alike between peridynamics and the classical model. And this also justifies why we can couple these two, whereas using a peridynamic region in the blended model allows us to still capture the same type of deformation on the hole at a much cheaper computational cost. Let's look into a second example, a quasi-static 3-point bending test. Here, there is a small crack on the bottom and the center. There is a concentrated load on the top, and there is 2 supports, A and B, on the bottom. The crack is going to propagate. So we are going to do is we are going to surround the crack tip, the region with the crack, with peridynamic nodes, and we are going to use finite element nodes elsewhere. But now, because the crack propagates, we are going to introduce a switching scheme where we're going to convert finite element nodes into peridynamic nodes as the crack propagates. And one question is to determine what's the size of that region, delta, that we need to use in order to surround the crack to mitigate or control coupling errors. So we are going to use, in this case, a splice approach. The splice is probably one of the simplest approaches. where you have an equation which takes two form, or the Penamics form in the Penamic region, or the classical form in the classical region, and there is no explicit mathematical coupling, although one can define a transition between the two where some interaction between the two domains happens. And then we have performance analysis that allows to control the out of balance error in an adaptive fashion on this type of coupling method. So here is a result where you can see from left to right, the crack is evolving. So actually, we always follow the cracks with this window. So even though it's the same window, it just moves with the crack. And we have two type of coupling approaches. One where the switching scheme one takes a distance of 2 delta for the transition. Then we have a distance of 3 delta. And the reason that we have these two is because our analysis showed that you have to account for high gradient regions in order to be able to estimate your errors. So you can see the color here are representing of these high gradients. So the farther the interface is from those high gradients, the smaller the coupling error would be. And this can be observed in the plot at the bottom where the switching scheme 2, which has a much larger region where the transition is farther from these high gradients, has a much more control of the coupling errors. So this is it's good. It works relatively well. However, there's all these considerations about how to decoupling, these coupling artifacts one has to deal. So a different approach is to try to avoid these challenges by completely moving to a different direction. And this is where we try to develop a code that it's fast and does not require coupling, and it has the following properties. It's going to be a code that is GPU enabled, so it's optimized for GPU acceleration. It's performance portable, so it runs efficiently across different machines, and it's exascale capable, so it's able to leverage leadership class supercomputers. And this is the code called Kavana PD. Now, there are other dynamics codes. For example, there's two popular codes developed at Sandia Labs, such as PDLAMS, which is based on LAMS, and Paradigm. And there is a bunch of research codes that I don't list here, but there's many dynamics codes that have been developed in the literature. However, most of the codes available, they're either not GPU capable or not portable. So, and these are features we want to preserve in our code. So Kavana PD is a relatively new peridynamic simulation code, which is built on top of a library Kavana, which is a performance portable particle simulation library, which is also based on Cocos, which are developed as part of the exascale computing project. So Kavana, as you can see in the illustration, it sits on top of, Kavana PD sits on top of Kavana, which give us performance portable particle and particle grid data structures, algorithms, and communications. It also relies on Cocos for on-node performance portability, for example, to be able to run on OpenMP for CPUs, CUDA for GPUs on Summit, and HIP for GPUs on Frontier, and this combines with MPI multi-node communication for multi-node computation. So we were targeting the large and very fast supercomputers we have at ORNL. First and foremost, Frontier is currently the second fastest supercomputer in the world. It's ranked number 2 in top 500, but actually it was the first machine to attain the exascale. And also Summit, which unfortunately has been decommissioned up to November 2024 to give place for an upcoming new machine. Now, if you're not familiar with the supercomputers, there's a ranking, and I'm going to show at it, but also I want to mention that we are not restricted to these supercomputers. We also want to be able to leverage other leadership class supercomputers such as El Capitan, Aurora, etc. And then going back to these rankings, so these rankings change every about 6 months, and this is the top 5 supercomputers right now up to the last ranking on November 2024. We have El Capitan at Lawrence Livermore National Laboratory that was deployed in 2024 with 11 million cores and achieving 1.7 exaflops. It was followed by Frontier at Oak Ridge National Laboratory, which was deployed in 2022 and was then the top 1 supercomputer, and then followed by Aurora at Argonne National Laboratory, Eagle at Microsoft Azure, and then we have HPC6 in Italy, and this is only the top 5, and the list keeps going. Now, let me show you some numerical examples run with Kavana PD. This is a famous case of a Kalthoff-Wilker fracture test. There is a steel plate that is pre-notch impacted in between the pre-notches. Here we are emulating impact with our velocity boundary conditions, and we have the damage propagation on the left and the strain energy density propagating on the right. This was run with 11.5 million particles. And in particular, looking to the strain energy density, it allows us to visualize the evolution of waves in the system that often triggers these cracks in nucleation and propagation. This is a second case of crack branching in soil-lime glass, where we have a thin glass plate and applied torsion on the top and bottom. The plate is pre-notched all the way to the middle, and then the crack is going to propagate, and then it's going to branch. And the good feature about peridynamics here is that we do not need to inform the system with some external rules to when the crack needs to propagate, how to propagate, or even how to branch. This just happens naturally from the mechanics of the system. And in this case, it's 1.7 million particles approximately. And the third example I want to show is a fragmenting cylinder due to internal pressure, as you can see illustrated on the left. And here is run with a little more than 500,000 particles. And you can see how, because of the pressure, the cylinder expands and then completely fractures. Now, looking to performance, we want acceleration. So we have here a comparison on Summit for GPUs versus CPUs, which we attain about 18 times speed up on the GPUs compared to the CPUs. In this case, we use a system with 6 million particles, and M is about 6, so it's about 1,000 neighbors per particle. Then we perform what's called M scaling. The M ratio is the ratio between the length scale delta and the grid spacing H. And if we keep, for example, delta fixed, you decrease H, the number of neighbors increase. So it becomes more and more expensive. So here we show that we are able to attain comparable CPU performance to LAMPS, which is a highly scalable code, but also we get very good acceleration in terms of GPUs, both on Frontier and Summit. We also look into weak scaling, which is to study the performance when both problem size and the resources increase, where you want to answer the question how well a system can handle a growing problem size by adding more processors, where the workload per processor remains constant. So you want to stay as close to a flat line, and you can see here for 1 million particles per GPU or CPU node, again with M equals 6, we get a pretty desirable result here. Similarly, another thing you want to study for scalability is strong scaling, where you study the performance for a fixed problem size with increasing number of resources. Here we try to answer the question how fast a fixed size problem can be solved when you increase the number of processors. And we study a system of 6 million particles with M equals 3 and up to 6 billion particles using up to 1,000 nodes of Summit in this case. And we also got pretty good results. And now we are moving forward towards further applications on different projects we have, including multi-physics and advanced manufacturing. Here are just two examples to demonstrate that. On the left, we have an example of thermal load cracking, where you see the temperature on the top and the damage on the bottom. You see as the temperature change because of some thermal shock, we obtain cracking. And on the right, we have a powder filling case for manufacturing, and you can see how the particles sit on the container. So we are keep advancing the capabilities in terms of physics and applications of Kavana PD. So I'd like to close here by saying that Kavana PD is a GPU-enabled, performance portable, and exascale capable mesh-free peridynamics code developed at ORNL. The Kavana PD ORNL co-developers mainly are Sam Reeve and Austin Isner. We also have Kavana PD is an open source, so it is on GitHub. You can download and run it. It's free to use. We also have another code that is based on MATLAB. It's called PD MATLAB 2D. It's a really good code to get introduced to peridynamics, either for educational and both research purposes, and it's mainly used for two-dimensional simulations for fracture. And then finally, I would like to acknowledge funding from the ORNL Laboratory Director Research and Development Program, the Exascale Computing Co-Design Center for Particle Applications project, the DOE Advanced Materials and Manufacturing Technologies Office, also the Advanced Scientific Computing Research or OSCAR program, as well as the Oak Ridge Leadership Computing Facility or OLCF at ORNL. Thank you very much for your attention. I'm happy to answer any questions you may have. Thank you.
Thank you so much, Pablo, for the great talk and giving a from the very basic knowledge of the dynamics all the way to this advancement. That was really wonderful. Thank you so much. So if you have any questions, this is the time that you can either raise your hand and then unmute yourself and ask question. For now, I have one question for you coming from our very close friend, Gilmo. He's asking that how are the boundary conditions treated?
Oh, that's a great question. Actually, boundary conditions in dynamics, I haven't discussed those. I didn't have the time. It's an ongoing research area. So, for example, there are cases where you could apply some non-local layer around the boundary. This allows you to establish the information needed for points that are near the surface. Because actually, the question, just to clarify a little more, it's that points near the boundary do not have a full neighborhood to interact with, and many times the material model parameters are determined by connecting to the classical theory with the assumption that we have a full neighborhood. So if you miss that, you are missing some potential interactions. So there have been different methods that have been used. For example, if you use a coupling approach, as I discussed there, because we use intentionally the classical model near the boundary, we can just use local boundary conditions. And this is one approach that people have used. Other approaches have been used if you have the information, you can apply a layer like a collar around your domain where you impose the information needed in a non-local fashion. And other approaches have been used to try to find a way to modify the interactions near the boundary so that you can use local boundary conditions. For example, one of the approaches that I have mentioned in this classification is this shrinking horizon approach, where again, you can reduce your non-locality near the boundary and then impose boundary conditions. For many of the simulations I have used, we have a free boundary, so it's closer to a Neumann type boundary condition. But there's still many methods, and it's still, I think, an area that people are considering.
Thank you. Any other questions? Anybody among the audiences, they have question that you want to ask? If not, maybe I'll ask a question. Yeah, so he's thanking you for your answer. So I was wondering that what are the recent advancement in terms of the size of the horizon and the microstructures and their relationship?
Yeah, that's also an excellent question. So one question that is often asked is how to determine this length scale. So one approach to answer the question that I like is saying that there's really not just one approach. There's like a few options. So for example, in some cases, in some scenarios, because we normalize some of the interactions to recover, or some of the constant to recover the desired behavior, it doesn't really matter what's the size of the non-locality, as long as it's large enough to allow for the complexity of the formation. In that regard, and before answering the other approaches, is that as in molecular dynamics, one requires a minimum number of interactions so be able to really capture the complexity of the formation of the material. So some people say that you need at least 3 neighbor interactions. In molecular dynamics, you may have 3 to 4. But for some systems, you may need to go to up to 4 neighbor interaction type, or even 6 or larger, depends on how much complexity you need. If you think about that, for fracture, the more interactions you have is the more connectivities you have, the more degrees of freedom you introduce for cracks to be able to propagate. So the less interactions you have per point, the more constrained the ability of the crack to propagate in different directions. So that's in general. Now, the other question is that some people think about cases where the non-local parameter can be used as a regularization type parameter. So it has that property. But then there are some cases, and we did some studies in that regard, where you can really tie the non-local parameter to some macro scale parameter. For example, we did a work on upscaling molecular dynamics, and there was a clear relation between a physical parameter of the interaction range in the atomistic system to the horizon. So I think there is not just one answer, but it really depends on the type of application and the scale you are want to use it for. And in that regard, I didn't have a slide for it, but another appealing feature of peridynamics is that the equation can really be used at multiple scales. So you can think of it as a multi-scale type model where I show simulation at the macro scale, I show simulation at the grain scale. You can also go farther below. So really the fact that you have this length scale in the system allows you to apply your model at different scales. So I think that's actually an appealing feature. And getting back to the original question, that also means that the answer to the question may rely or may depend on which scale we are talking about.
Thank you. Thank you so much. So anybody, if you have any question for now, I guess either of our wonderful speakers, this is the time to ask before we wrap up. If there aren't any more questions, if you have any, I guess you can reach out to them and ask them directly. Or if you are interested in collaborating or using any of the tools, feel free to reach out to our speakers. Yeah, so thank you so much again to all of you, all the speakers, and then also the audiences for participating. I hope that you found it beneficial. So let's thank the speaker one more time.